Hello and welcome to this revision session on the Cosmology section of the AQA Astrophysics option module. So the first part of this revision session is going to be looking at the Doppler effect. So all electromagnetic waves have a frequency and a wavelength which allows for physicists to measure these quantities. Now the motion of either an observer or an emitter can change the wavelength and frequency of the wave detected. Now we call this the Doppler effect. So the Doppler effect is an observational effect as it only changes the observed properties of a wave and not its actual properties, and it is caused by the relative motion between the observer and emitter of the radiation. So this can cause the observed frequency and wavelength of the wave to be altered. So we can look at this with the example of a person coming towards an observer on a motorbike. Now as the space between the emitter and observer decreases, it will push any wave emitted closer together, so the frequency of the wave gets bigger and the wavelength gets smaller. Now if the two objects, the thing emitting the radiation and the thing observing the radiation, has no change in distance between the two of them, there's no change in wavelength or frequency, there is no Doppler effect. But if the emitter or observer is moving away from the other, the space between the emitter and observer increases, which spreads the wave out. So this means the frequency gets lower and the wavelength gets bigger. This is the Doppler effect. So the Doppler effect is when the wavelength and frequency of a wave is altered by the relative movement of the source or the observer. Now when the source or observer is receding, moving away from another, the wavelength is longer than it should be and the frequency is lower. Now when the source or observer is moving towards the other, the wavelength is shorter than it should be and the frequency is higher. Now this is important when we consider visible light, because all waves experience the Doppler effect, including visible light, but humans experience the wavelength and frequency of the visible light wave as colour. So what we know is that a long wavelength visible light wave is interpreted as red light, whilst a short wavelength visible light wave is interpreted as blue light, which you can see on the following image here. Our longer wavelength waves are red and our shorter wavelength waves are blue. So now let's consider the Doppler effect from the perspective of colour. So as the space between an emitter and observer decreases as they're moving towards each other, if there is a light wave emitted, this means that the frequency of the light wave gets bigger, the wavelength gets smaller, so the light appears bluer. Now this is called blue shift. Now if the two objects, the emitter and the observer, are moving further apart, well, the space between the two objects increases, so therefore the frequency gets lower and the wavelength gets bigger, so the light appears redder to the perception of the observer. We call this redshift. So redshift is the Doppler effect for light. Now as light is a wave, it experiences the Doppler effect if either or both an observer or an emission source are in relative motion. So if the emitter and observer are moving apart, the wavelength is longer and the frequency is shorter, so it appears redder to humans. This is redshift. If the two objects are moving closer together, the wavelength is shorter and the frequency is longer, so it appears bluer to humans. This is blue shift. So we can observe this in the example of distant objects in our universe. If an object is moving towards an observer, it will appear bluer than the observer expects. But if an object is moving away from an observer, it will appear redder than the observer expects. Now we can determine if a stellar object is red shifting or blue shifting by comparing the spectral lines of emission with a known source and seeing if there's a difference to the emission spectrum lines of that distant object. Now this occurs as the absorption spectrum of an element is the same regardless of motion, location or temperature in the universe. So we can use a lab-based sample of the predicted composition of a stellar object to observe the effect of redshift or blue shift. Now this can take place because we can see if there's a change in reference points in the absorption spectra of distant galaxies compared to the absorption spectra of a stationary sample of matter in the lab. Now the most commonly used reference points are the Balmer lines, the visible absorption lines of hydrogen, because hydrogen is the most common element in the universe. Now we can calculate the amount of redshift a galaxy exhibits, Z, with the following equation. Z equals the change in wavelength over wavelength, which equals the change in frequency over frequency, frequency, which is equal to the velocity of the moving object divided by the speed of light. Now it's important to remember that in this equation it will only work if the recession velocity, the motion of either the observer or the emitter, is much less than the speed of light, which is a very important idea. Now you are given these equations in your examination, but you've got to be able to use these equations correctly. So you've got to be able to equate the different equations of redshift. So you can say that a change in wavelength over wavelength is equal to the velocity over the speed of light, or you could say change in frequency over frequency is equal to the change in wavelength over wavelength, or any iteration you would like, but you can equate them to each other. Now Z is a quantitative measure of the redshift effect, and it has no units. It is a ratio. Now it can be considered to be the absolute change in wavelength, but only the approximate change in frequency due to relativistic effects. Now Z is positive if the object is redshifting, but Z is negative if the object is blue shifting. Now Z can also be a measure of time, since the light takes time to reach us. So if you see the notation Z equals 0, it indicates the present time. Now the highest redshift ever recorded was due to the cosmic microwave background radiation, with a redshift of 1089, whilst the highest Z value for a galaxy is 11.1. Now we can look at carrying out a calculation with the following example. In a lab sample, the hydrogen alpha spectral lines at a wavelength of 656.285 nanometers. In the spectrum from a nearby star, this line is observed at a wavelength of 656.315 nanometers. How fast is this star moving, and in what direction? Well, the first thing you can note is that the wavelength of the star is longer than it should be, so it must be moving away. Now the next thing you can do is then you can work out what V is going to be by thinking of the equation change in lambda over lambda is equal to V over C. So therefore V is equal to C times by change in lambda over lambda. Now as this is a ratio, there's no need to change your wavelengths into from nanometers into meters, because they'll just cancel through each other anyway. So you work your answer out to be 13700 meters per second, or 13.7 kilometers per second. Now there are two examples of redshift detected in astrophysics. There's the cosmological redshift, and there's also stellar redshift. The cosmological redshift is redshift detected on distant galaxies, while stellar redshift is redshift detected on nearby stars. Now cosmological redshift is detected on all galaxies except the Andromeda, whilst stellar redshift is detected on certain stars, especially pairs of stars called binary stars. Now the cosmological redshift allows us for further proof of the expansion of the universe and the hot Big Bang model, while stellar redshift allows us to determine properties about stars. So let's consider stellar redshift. So let's consider the rotation of a star in this concept of stellar redshift. Now we will observe red and blue shift with stars due to their rotational motion. So as the star rotates, the part of the star will be moving towards an observer, such as a satellite, and as the star rotates, part of the star will be moving away from an observer, such as a satellite. So the part of the star moving towards us will produce light which is slightly blue shifted, so the light emitted from this part of the star will be slightly bluer, whilst the part of the star rotating away from us will have a slight redshift in the light emitted, which will be slightly redder, which is how we can determine stellar rotation. Now we can also observe this idea of redshift and blue shift with binary stars. So binary stars are when you have two stars orbiting around a common centre of mass as a pair. Now this is an extremely common astronomical event. Now we tend to denote the larger and brighter of the two stars as the A star, and the smaller and dimmer of the two stars as the B star. So we've got Sirius A and Sirius B as shown in this diagram. Now we need to be sure though, when we are observing these binary stars from Earth, that these are actually a binary system and not a phenomenon caused by optical inaccuracy. So we've got to use redshift as when the two stars orbit about one another, one will be orbiting towards us and one will be orbiting away from us. So the star which will be moving towards us would blue shift, the light from the star would blue shift, and the star observed to be moving away from us would have light emitted which is redshifted. So in our line of sight, one star will in fact pass in front of the other, causing an eclipse, which you can see in the simplified light curve from an eclipse and binary system shown below. So the apparent magnitude scale increases going downwards, i.e. the dips in the graph correspond to the light dimming, and in this example the two stars have different surface temperatures, so actually might emit different amounts of light anywhere per unit surface area. So when the apparent magnitude is 3.30, the system is at its brightest as both stars can be seen from Earth. Now the deeper the dips are caused by the cooler star passing in front of the hotter star, so the apparent magnitude is 3.60. Now the shallower dips to 3.45 occur when the hotter star passes in front of the cooler. Now if the light from one star is analysed in more detail, the shift in wavelength of one particular spectral line can be measured as the star follows its circular orbit. So the peak in the graph occurs when the star is receding from our point of view at its maximum velocity, and the eclipse occurs when the star is moving at right angles to our line of sight. So you can see from this particular image that the orbital period will be 8 days, as this is how long it takes before the wave repeats itself. You can then use your Doppler equation to calculate the maximum recession velocity, which is equal to the orbital speed of our star, by doing change in lambda over lambda equals v over c to work out what v would be. You can then, with the orbital speed and the time period, determine the diameter of the orbit by using a circular motion equation, where the circumference of the orbit is equal to the orbital speed times by the orbital period. And so as a result, you can work out your diameter of your orbit by doing your circumference divided by pi. So now let's look at Hubble's law. Now Edwin Hubble was an American astronomer who lived in the early 20th century. Now he made a huge impact on astronomy. Now Hubble studied the light spectra of many galaxies and could identify prominent spectral lines. Now he soon realized that all galaxies were redshifted. So from the redshift equation, it shows that all galaxies were moving away from the Earth. So all galaxies have a recession velocity. Now Hubble deduced the distance from Earth that these galaxies have by using separate variable stars as standard candles. Now Hubble soon realized there was a link between the amount of redshift or recession velocity and the distance it is from the Earth, which he called Hubble's law. Now Hubble's law states that the greater the distance from the Earth, the greater the absorption spectrum from a galaxy is redshifted, the greater the recession velocity of a galaxy, which in equation form is given with the equation recession velocity is equal to the Hubble constant times by the distance from the Earth, which is given to you in your examination booklet. Now you've got to be able to use this equation, not memorize it. Now AQA states that the Hubble's constant is 65 kilometers per second per megaparsec. Now it's important to know that as we move forward here, okay, that the further the galaxy is from the Earth, the higher the recession velocity, whilst the closer the galaxy is to the Earth, the lower the recession velocity. Now examination questions can ask you to determine the recession velocity via the redshift equation and then use this value in this equation. Now it's important to note that the distance between the Earth and galaxies is very difficult to measure, so astronomers disagree greatly on the value of h. Now originally Hubble thought that the Hubble constant lied between 50 and 100 kilometers per second per megaparsec. It's now thought that it lies between 65 and 80 kilometers per second per megaparsecs, and we now feel it lies at approximately 70. Now again, in the AQA examination, we like to use a standard value of 65 kilometers per second per megaparsec. Now when we consider Hubble's law, this implies several ideas about the universe. Now Hubble's law states that the recession velocity of a galaxy is directly proportional to its distance from the Earth. Now in this particular graph, the gradient of the line is the Hubble constant. Now we believe this effect is due to the cosmological redshift. So cosmological redshift is due to the space in between the galaxies, known as voids, expanding, which causes the galaxies to recede from each other with a recession velocity. So if we can imagine galaxy 1 and galaxy 2 here, the space in between the two galaxies is expanding. This causes the galaxies to move away from each other. Now this effect is observed from both galaxies, galaxies, so it makes it appear that all galaxies are moving away from each other. Now this effect is noticed in every single part of the universe, so our cosmological principle, where there's no special place in the universe, is still obeyed. It's an illusion where it appears where you are in a special place in the universe. Hubble's law is observed anywhere in the universe. So let's just clarify what Hubble's law is. The greater the space between galaxies, the more the expansion of space, the greater speed at which galaxies receive from each other. That is Hubble's law. Now it's important to note that as this line for Hubble's law is straight, it assumes that the expansion of the universe is occurring at the same rate in all space and all time, which is a further implication from the cosmological principle. But also we can note that because we have velocity on the y-axis and distance on the x-axis, we can also work out time, because time is equal to distance over velocity, so time in this example is equal to 1 over gradient, where the gradient is the Hubble's constant. So therefore time is equal to 1 over Hubble's constant. So we use this time to have the first estimate for the age of the universe. Now for the answer to be calculated in seconds, the recession velocity must be converted into meters per second, and the distance from the Earth must be converted into meters. So for answers to be calculated into seconds, the units of Hubble's constant must now be in seconds to the -1, because we have meters per second over meters. That gives our time in seconds. But there are two issues when we calculate a value for the age of the universe with this method. The first issue is it assumes that the universe has been expanding constantly, which we now think not to be true. And secondly, the value of Hubble's constant is a great area of debate in cosmology. So this leads to this calculation being an overestimate for the age of the universe, as we think the expansion of the universe is increasing in rate. So we actually now refer to this value as the Hubble time. So let's look at an example question. So how far away is a supernova, which has a redshift of Z equals 0.45, and can we use it to work out the age of the universe? So we say Z equals V over C, so therefore we can therefore say V is going to equal to Z times by C, so therefore we can work it out to be 1.35 times 10 to the 5 kilometers per second. Now as we know in Hubble's law, V equals HD, D equals V over H, so therefore do 1.35 times 10 to the 5 over 71, the value we're going to use for Hubble's constant in this example, so we get 1900 megaparsecs, and therefore we can say that the age of the universe is going to be 1 over Hubble's constant. Now again, we've used Hubble's constant to be 71 in this particular question, so we've got to convert Hubble's constant to seconds to the -1, which we can do very quickly by dividing that value by 3.09 times 10 to the 19. We do 1 over that value and we get 4.35 times 10 to the 17 seconds. Now here's a sample scatter of the data Hubble used. Now the data suggests that the universe is expanding. It's like being an average runner in a race. Those in front of you are faster than you and moving away from you, but you are faster than those behind you and you're moving away from them. So from your point of view, it appears that everyone's moving away from you. Now, it's important to note that Hubble's law suggests that once there was one common starting point, so as the distance between the galaxies was 0, the time since the beginning of the expansion, the age of the universe, can be found by dividing the distance to a galaxy by its recession velocity. So it's going to be equal to D over V, 1 over H, which gives an age of about 15 billion years. But this equation assumes the expansion rate is constant. Now, recent evidence suggests that the rate of expansion is increasing, which relates to something called dark energy. So the expansion of the universe causes objects to be moving further away from each other. So if we consider the observable universe, which is a sphere with a radius equal to the maximum distance that light can travel during the existence of the universe. Now we believe the observable universe is about 47 billion light years across, but we only think the universe is 13.7 billion years old. So the difference in values is due to the expansion of the universe increasing the size of the observable universe, because via redshift, Hubble derived the further away a galaxy is, the greater the redshift observed, the faster the object is moving away from us. But this allows physicists to speculate. If all objects are moving away from each other now, were they all condensed in one region of space? So the proposed model to explain the expansion of the universe from one point was called the Big Bang Theory. So the Big Bang Theory says the universe had a beginning, and the universe started off very hot and very dense and has been expanding ever since. Now all matter was created at the start, so the matter density of the universe is currently going down. So in the beginning, before the Big Bang, there was nothing. Time and space didn't exist. There was nothing to consider. Then the universe comes into existence. Now, even though we call this the Big Bang, that's just because we associate a bang with something happening and energy being released. In reality, all of matter just slipped into existence. In one instance, all of it appeared. So at the Big Bang, all of time, space, energy and matter was created. The universe was super dense and super hot, which is a fundamental principle of the hot Big Bang model. All of the universe was created in a super hot, super dense instant. The universe then undergoes a super fast exponential expansion called inflation. So the universe increases in size very quickly and it cools down as this happens. Now, we believe inflation happened to allow for galaxies to form in the universe, because quantum mechanical fluctuations produce a density imbalance which leads to galaxies and voids. Now, after 1 second, electrons, protons and neutrons form in the universe, but the universe is still too hot for the particles to form atoms. So the universe continues to expand and cool down. Now, after about 3 minutes, a rapidly cooling and expanding universe allows neutrons and protons to clump together to make nuclei. But there is still no such thing as electromagnetic radiation. Matter and energy are still coupled, so energy cannot flow through the universe. Now, after about 300,000 years, the electrons combine with nuclei to form atoms, and now electromagnetic radiation is released for the first time. So this allows radiation to be released and emitted, which we now observe as the cosmic microwave background. So this image can be found in all directions of the universe. It's been extremely redshifted and has a peak temperature of 3 Kelvin. Now, the cosmological background radiation could only have been formed in the Big Bang model. Now, the temperature of the universe is high enough at this point for 25% of the hydrogen of the universe to fuse into helium. Now, these conditions are only present for enough time to convert 25% as the universe continues to expand and cool. So the abundance of hydrogen and helium can only be explained by the Big Bang model. So just to clarify before we move on, the cosmological background is an image of the universe aged 300,000 years old. Now, after 1 billion years, the hydrogen found in clouds clumps together under gravity the first time, and you get your first protostars and proto-galaxies. So we now have our first stellar cycle. This forms massive stars which quickly move through the stellar cycle and implode via supernovae, which produces many quasars in the universe. Now, after about 10 billion years, we've now got our first heavier elements produced in those star deaths. Now, the second stellar cycle occurs and the universe becomes more and more clumpy. There are regions of galaxies and voids in the universe. So now, 13.7 billion years after the Big Bang, we are currently here with many stars, galaxies and other objects formed. So the universe started off as a hot, very dense universe which was very uniform. Now we live in a universe which is cold, much larger and is very clumpy. There's areas of matter and areas of space. So it's very important to remember that the early universe was very hot, very dense and very uniform. And in addition, the observable universe is very small when it was very, very young. So how do we know that the Big Bang occurred? Now, the Big Bang was not an explosion, but there's no other way to visualize this idea. Now, the Big Bang released radiation about 300,000 years after the initial point of formation, as before then electromagnetic waves were coupled with matter. So when the universe cools sufficiently for matter and radiation to decouple, the combination of protons and electrons form neutral atoms. So this radiation is found in all directions we observe. It's cosmic and it can be considered to have its own blackbody radiation curve. Now, this curve has a peak temperature of 3 Kelvin. Now, it was originally released as gamma waves, but over time, because as the universe has expanded and expanded and expanded, these gamma waves have turned into microwaves, so they now have formed the cosmological microwave background. So this is evidence which provides evidence for the Big Bang theory. So in millions of years, as the universe continues to expand, it will become the cosmic radio wave background, and this is why space is not found to be at absolute zero. It's at 2.7 Kelvin because it's heated by the cosmological microwave background. The fabric of our universe is still being heated by the afterglow of the Big Bang. Now, like I said before, it can be considered the universe has its own blackbody radiation curve with a peak temperature of 2.7 Kelvin. So the cosmological microwave background is the same in all directions. Shown must have been coming from a single starting point of creation. We are in fact looking into the eyes of God when we see these particular images. So the other piece of evidence for the hot Big Bang model is that the conditions of the universe were extremely hot and extremely dense. So these conditions were high enough for fusion to occur. So this caused the first protons, hydrogen, to fuse into helium. This meant that the early universe was made of hydrogen and helium. So we can now see we're producing hydrogen and helium, but over time the universe cooled when it expanded. So this meant fusion could no longer occur. This meant that the universe would only have hydrogen and helium until the first stars were made. Now, the Big Bang model predicts at the rate of expansion that there was only enough time to make 25% of the universe into helium, and there was no time to produce any larger elements. So the universe, in theory, should be 75% hydrogen and 25% helium, which is what we observe. So this is further experimental proof of the hot Big Bang model. Now, the universe expanded and cooled too rapidly for any creation of large nuclei and resulted in the relative abundance of hydrogen and helium at a 3-to-1 ratio spread uniformly through the universe, which, as we said before, is consistent with observation. So our proof of the Big Bang comes in three forms. The evidence 1, redshift. Evidence 2, the cosmological microwave background. And evidence 3, the relative abundance of hydrogen and helium. Now, the idea of the Big Bang taking place allows us to consider how the universe began, but we've also pondered what will happen to the universe in the distant future. So to understand what will happen, we've got to consider the two forces acting on the universal scale. So we've got gravitational attraction pulling the universe inwards, caused by dark matter and visible matter of the universe, and we've got dark energy causing the expansion of the universe. So the relative sizes of dark energy and dark matter will lead to how the universe will evolve in the distant future. If the expansion force is larger than the attractive force, the universe will expand forever. This is called the open universe. Now, if the expansion force is the same size as the attractive force, the universe will stay the same size. This is called the flat universe. And if the expansion force is smaller than the attractive force, then the universe will decrease back to a singularity. This is called the closed universe. So you've got three possible options of how the universe will evolve. Now, for a long time, astrophysics didn't know which model the universe will take. However, this changed when we observed distant standard candles in our own universe. So the observations of distant supernovae in 1999 indicate the expansion of the universe is increasing, implying an open universe. So if we consider our Hubble's law graph, as we know, Hubble's law states that recession velocity is directly proportional to the distance from the Earth, implying the universe has an expansion rate which is constant. We've got a straight line of best fit. So we can extrapolate the trend for more distant objects. So in 1999 we measured the most distant type 1a supernovae. Now, if Hubble's law is to be obeyed, they should be found on the trend line here. However, when the redshift of the supernovae were observed, this showed that the objects were receding faster than they should do. So they were redshifted more than we expected. So this implies that the Hubble's law graph trend is increasing. This implies that the expansion rate of the universe is accelerating. Now, this is controversial as we don't know why this is the case. We don't understand the physics of this acceleration. Now, this conclusion was further confirmed with redshift observed from quasars, which are even more distant objects than the type 1a supernovae observed in 1999. So just to clarify, the type 1a supernovae had greater redshifts than predicted by Hubble's law, indicating the expansion of the universe is not constant, rather it is accelerating. Now, this is controversial as the concept of dark energy is not fully understood. It's thought that the expansion of the universe was decelerating until about 5 billion years ago. The expansion of the universe is now accelerating. Now, dark energy is accepted to exist in the universe according to current thinking, but we don't know its mechanism, origin, or interaction with the rest of the universe. We are in the dark regarding it. Now, we are unsure as to how the universe will evolve because we're close to the start of the universe. The next thing to look at are quasars. Now, quasars are only observed in the distant universe, implying that they were only formed in the early universe, which is very, very useful as the conditions produced by quasars are not favourable for life to develop, because quasars are supermassive black holes surrounded by a sea of gas and dust. The gas and dust get accelerated towards the black hole, causing gamma waves to be emitted by the quasar. So we currently believe that there's a supermassive black hole in the center of every galaxy, but only a select number emit material from their nuclei. So we believe that their supermassive black holes 10 to the 6 times more massive than that of the Sun. Now we call galactic centers which emit material active galactic nuclei, and the galaxies which contain an AGN an active galaxy. Now we currently believe that there's a supermassive black hole in the center of every large galaxy, but only a select number emit material from their nuclei. Now the Milky Way has a supermassive black hole at its center, which you can see is located in its own galactical bulge. But our galaxy is not an active galaxy, as we think this could change when it collides with the Andromeda galaxy. Now it's useful that our galaxy is not an active galaxy, as the emission of material will cause a mass extinction event on the Earth if the beam was in our direction. Now this image shows us a galactic cluster which contains an AGN. Now you can observe the emission in the radio spectrum. Now that's a very important idea because quasars and AGN are very bright radio source emitters. Now AGN do not have the same power as quasars, but they're still very powerful. Now since quasars are standard candles, we can use the inverse square law to determine either the power of a quasar or its distance from the Earth. Now previously we'd stated that the brightness of an object observed on the Earth is dependent on the intensity and the distance from the Earth. So we can show through the following equation that intensity is equal to power over 4 pi d squared, where d is the separation between the object and the Earth. So therefore power is equal to intensity times by 4 pi d squared. So when a quasar has the same observed brightness or intensity as another stellar object, we can use a ratio of this equation. But this equation will only work if the quasar has the same intensity or brightness as the other stellar object. So we can say the power of the quasar over the distance to the quasar squared is equal to the power of the other object divided by the distance to the other object squared. So because the intensity is the same on both sides of the equation, it can cancel out. So you can say here that the power of the quasar over the power of the object is equal to the distance to the quasar divided by the distance to the object squared. So let's look at an example question regarding this concept. A quasar has the same intensity as a star. The star is 20,000 light years away and has the same power output as the Sun. The quasar has a redshift given a distance from the Earth of 1 times 10 to the 10 light years. So what is the power of the quasar? Well, we know that the intensity cancels out because it's the same on both sides. So the power of the quasar over the distance to the quasar squared is equal to the power of the star over the distance to the star squared. So we can rearrange that and make power of the quasar the subject of your equation, pop all your values in, work it through, and you get an answer of 1 times 10 to the 38 watts, which is about 10 times brighter than the entire power of the Milky Way. So it's very likely to be right, because we know that a quasar is a super bright radio source, so it's likely to have a power a lot brighter than a galaxy. Now the final topic we're going to look at in today's revision session is the detection of an exoplanet. Now an exoplanet is a planet located outside the solar system orbiting a star that is not our Sun. So the definition of an exoplanet is a planet which is located around a star which is not the Sun. Now the first exoplanet we discovered orbiting a main sequence star was the Sun-like 51 Pegasi, and it marked a breakthrough in astronomical research because it found a prototype for a class of planets called hot Jupiters. Now some exoplanets have been imaged directly by telescopes, but the vast majority have been detected through indirect methods such as the transit method and the radial velocity method. So as you can see in the following image, there's a variety of different methods that we use to detect exoplanets in 2021. Now some exoplanets have been imaged directly, but the vast majority are used by indirect methods, so we've got to use multiple methods to confirm the existence of an exoplanet. This is because there's an associated issue with each separate method of exoplanet detection. Now if we just consider an exoplanet orbiting a star which is not our Sun, it's very difficult to detect an exoplanet directly with a telescope based on or around the Earth, because firstly the exoplanets are orbiting a star which is much brighter than they are, so the exoplanets are drowned out by the bright light from the star which they are orbiting. The second issue is that the angular separation between the star and the exoplanet is much smaller than the minimum angular separation of our telescopes. Now, planets far enough away from a star to be resolved are likely to be very dim because they're so far away from their star they'll not reflect much light. Now, despite this issue, several exoplanets have been directly imaged. They tend to be very large and in very large orbits, and they also tend to be very hot, so they can be found from their infrared emission rather than the reflected light from their star. Now, it also helps if the planet orbits a brown dwarf or another dim star. Now, technology has advanced and various masking techniques have been developed to block out the light from stars so that planets orbited may be directly imaged, but only the largest, hottest exoplanets which orbit at a large distance from their star can be detected directly. So this method can detect Jupiter-like planets as opposed to Earth-like planets. So other methods must be used to detect exoplanets. So a different method to detect an exoplanet is called the radial velocity method. Now, this uses the Doppler effect to detect exoplanets. So when a planet orbits a star, the star and the planet co-orbit around a common centre of mass, which is very close to the star's core. That's because most of the mass of the star system is found in the star. So this causes the star to have a slight variation and wobble on its axis whilst the exoplanet orbits the star. So as the star wobbles towards our telescopes on Earth, the electromagnetic spectrum it emits appears to be blue shifted, whilst as the star wobbles away from our telescope on Earth, its electromagnetic radiation it emits appears to be red shifted. Now, this red shift and blue shift is periodic, as the star will periodically wobble as the star orbits. So we can work things out with the Doppler spectroscopy. Now, the larger the planet, the greater the wobble of the star, so the greater the red shift and blue shift. The smaller the planet, the less the wobble of the star, and the less the red and blue shift. So the mass of the planet can be determined via this methodology. So this red shifting and blue shifting is periodic, and from this the minimum mass of the planet can be detected. However, there are issues with this method. This effect is only noticeable when the exoplanet is close in size to that of the star. So this method can only detect Jupiter-like planets as opposed to Earth-like planets. The second issue is that the movement of the star needs to be aligned with the observer's line of sight. If a planet orbits the star perpendicular to our line of sight, there is no detectable shift. So to get a measurable result, the star must orbit edge on to the viewpoint of the Earth. So this means that if a planet orbits the star perpendicular to our line of sight, there's no detectable shift. This means another method is needed to detect exoplanets. So a different method is used, which is called the transit method. So the transit method measures the change in apparent magnitude in exoplanet transits in front of the star from the view of the Earth as it orbits the star. So as the exoplanet moves across the star, it will show that it appears to be a dimming in the output of the star. So at this point, there is no change in the apparent magnitude of the star to the telescope on Earth. Here, as the exoplanet passes in front of the star, there's a dip in the apparent magnitude of the star to the telescope on Earth. So the larger the exoplanet compared to the star, the greater the dip in apparent magnitude. The further away the exoplanet from the star, the longer the dip in apparent magnitude. And once the star passes across the star, there's then no change in apparent magnitude. The apparent magnitude returns to its original value. So you can look at the light curves of stars. So this star has several planets orbiting around it, and they were detected by the change in luminosity they appear to cause to the star when they pass in the plane of observation between the Earth and the star. So the bigger a planet, the larger the drop in apparent magnitude, and the further away a planet from the star, the longer the drop in apparent magnitude. So this method allows you to determine the radius of a planet and its orbital distance from the star. So you can observe this with the following images shown here. So you can see that as the star moves across, as the planet moves across the star, you observe a dip in brightness in the output of the star. And again, you can see here that as the planet moves across the star, you will have this dip in the light curve. Now, it's important to also note that many other processes can cause this shape of light curve, such as a sunspot or a variation in the output of the star itself. And other stellar objects can cause this dip in apparent magnitude. But the existence of an exoplanet is confirmed if these dips in the light curve are periodic. Now, at least 3 periodic dips are needed to establish a planet. So this can lead to various issues. So number one issue in the transit method is that a dip in light curve can be caused by other effects. Issue 2 is that periodic dips can take a very long time to establish, so it can take many years to confirm the existence of an exoplanet. And Issue 3 is that alignment must be correct for a planet and star to eclipse in the plane of the Earth, which is quite unlikely. So even if it is aligned, the transit is likely to only last a tiny fraction of the whole orbital period, so it makes it very easy to miss if you're not studying the star closely. So this alignment issue means that this method can only be used to confirm existing exoplanets. So if no dip is observed, it doesn't not always mean that there's no planet, just not that's aligned with us. So this means that the transit method can only confirm the existence of exoplanets and not rule out any star systems. So this tells us that multiple methods of detection must be used to find out as much information as possible about an exoplanet and to ensure that issues with detection are not a hindrance. So let's summarize what we've looked at in today's revision session. That in Redshift we know that delta F over F equals V over C, and Z equals change in lambda over lambda, which equals to minus V over C, which can only work if V is much smaller than C, and you can also do calculations on binary stars viewed in the plane of orbit. That Redshift is equal to V equals HD, and the simple interpretation as expansion of the universe, estimation of the age of the universe, and assuming H is constant. We can have a qualitative treatment of the Big Bang Theory, including evidence from the cosmological microwave background radiation and the relative abundance of hydrogen and helium. We know quasars are the most distant measurable objects, and the discovery of quasars was due to the fact they are bright radio sources. Quasars show large optical redshifts, and estimations involve distance and power output, and the formation of quasars from active supermassive black holes. You should find how understanding the difficulties in the direct detection of exoplanets, and the detection techniques are limited to the variation in Doppler Effect, the Doppler shift, the radial velocity method, and the transit method, and you should be able to recognize and show a typical light curve for the transit method. So, I hope you've enjoyed today's revision session on cosmology in the astrophysics option of AQA A-Level Physics. Thank you very much for watching, and as always, have a lovely day.